He's in?
Yeah.
Okay. But why they are recording and we didn't start it yet?
Okay, I don't know why I will. Okay, I see. Besides being mute, I was also deaf, so not easy. But now I'm fully there with you. Can you hear me?
Yeah.
Yeah, we
Right.
can hear you now.
Obviously, if I say, "Can you hear me?" and you can't hear me, you don't hear me. So okay. But now you can. All right. Sorry about that. Let's see. Last time I saw you, we were talking about waves in a gas. We weren't really talking about waves in a gas, but more like about pressure in a gas and how that's related to the speed at which particles of that gas, well, I shouldn't say particles, we're not talking about molecules, but a given parcel, a given portion of that gas might be moving around, for example, because it's hit by a wave, okay, which is ultimately what we are interested in. And if I call v the velocity with which those waves, not those waves, sorry, the velocity with which the mass moves around, so it's really a velocity associated with a displacement of mass. It's not a velocity of propagation. So if I call that v, and notice that I'm underlining it because we are now finally dealing with vector, okay? V is a vector. In 3D, it's gonna have three components in three-dimensional space. So if I call it V, then we've discovered that, well, actually, let's start with another vector. Let's talk first about F, which is the force that sets those particles in motion. That force is equal to the gradient of the pressure. If I divide, and I have to divide it by the volume, capital V. So if now, and here I have my velocity V, I apply Newton's second law, to this, I do a force balance. Well, F can be replaced with mass times acceleration. This is just another way of writing acceleration, okay? The time derivative of velocity is acceleration. So that coincides again with the gradient of the pressure. And of course, the ratio of mass over volume is density. So we can rewrite this equation in a slightly simpler form like that. So what does this mean physically? Because we are in a fluid now, we have this quantity P, which is the force per unit area that you will measure if you cut abstractly, conceptually, imagine to take a surface across this gas somewhere, and if you were able to measure the force that one side of that surface exerts on the other side, okay? So, you know, like if you imagine, you know, if you are in the ocean and you go at you swim at a certain depth, if you could measure the force that the mass that is above you exerts on the mass that is below you, and then you divide it by the area over which you make your measurement, you get a pressure. It's a pressure of the water that's above to the water that's below. In that case, the governing entity is weight, okay, is gravitational attraction. But it doesn't need to be gravitational attraction. For example, you might neglect gravitational attraction. You might be in your room listening to music, and the speaker, as it moves around, it also exerts a force on the air that is next to it that can be expressed as a pressure, you know, if you divide by the speaker's area. So what this equation says is that those particles of air just next to your speaker will receive an acceleration. We start moving with an acceleration that has to coincide, because of Newton's laws, with the gradient of the pressure divided by rho. Okay? The gradient is a measure of how the pressure changes in space. Okay, it's a derivative. It's a set of derivative. Remember, this is just del over del x, del over del y, del over the z of p, or which is the same. I'm writing the vector component by component, right? And I'm not going to do it in this course, but if you revise your math, and you can check that out on that website that I gave you the other day, khanacademy.org. I'm sure that you will find a nice video somewhere to explain you some geometrical property of the gradients. But basically, the gradient is a vector that always points in the direction of maximum change, okay? So if I'm, you know, like behind me is a window and it's kind of cold outside, and on the other side, it's the middle of the building and it's warmer. So the gradient of temperature would point in that direction from the window where it's cold to the other side of the room where there's a heater and it's warm. It's not true the heater is here, but you get my idea. And the same thing for pressure, okay? It points in the direction where the change is faster. Okay, so if you are listening to music right in front of your speaker, the gradient of pressure will probably point towards you. Okay, so what we discovered now, you know, we can forget about F, we can forget about force, and just deal with pressure and acceleration. And at every point in the medium that we are studying, this equation has to hold, okay? So that is the first ingredient of what we are going to do. And I'm going to make some room. No. All right. Now, the next, so that's Newton's law. It's basically all we need to obtain that equation is Newton's second law and the definition of pressure and just a little bit of math, of geometry. So now we had some other knowledge about our gas that we should also use. Remember, what do we want to do? Remember what we did for the string. For the fixed string, we wanted to obtain a differential equation with one unknown function, displacement. And then predicting how the string will move, will deform over time, is the same as solving the differential equation. It amounts to solving that differential equation. Now, we basically want to follow the same strategy. We have already an equation that involves some derivatives. You can call it a differential equation, but it's not, we cannot solve it right away because we have the velocity here, we have pressure here, they're both unknown. We can't just do the math, right? We have two unknown functions, one equation, we need some more information. Basically, we want a differential equation with one unknown function, and then we can start using the tools that we have learned to solve it, okay? So how do we read either of velocity, either write everything in terms of velocity, write everything in terms of pressure? How do we do that? Well, we are dealing with a gas, right? So it's natural to use thermodynamics. The pressure, the volume, the temperature of a gas are related together by some empirical laws that are the laws of thermodynamics, and that are independent from, we might say that they are independent, or in any case, they provide some further information about the system than the information that's already contained in Newton's law. Okay, and basically the fundamental equation in thermodynamics that is relevant is that the pressure, okay, the pressure is really the crux of the matter here, times the volume is a constant. Well, if the temperature is constant, okay? So I think it's already quite interesting to consider the case where temperature is constant, because think of the experiments we are talking about. I mean, basically the propagation of an acoustic wave, we know it's even not that hard to measure the velocity of sound, that it was measured centuries ago already. It's hundreds of meters per second. I think it's about 330 meters per second or something like that. So we are talking about relatively fast processes, right? If I talk to you, you hear me right away. If I'm very far, maybe you will hear me screaming 1 second later. But that's very fast compared to how fast temperature will change in normal atmospheric conditions. So we can, if we are interested, say, in studying how sound propagates in a room, typical acoustics problem, or how fast seismic elastic wave propagates in the ocean, a typical problem for exploration seismologists, everything is much faster than the time it takes for temperature to change. So it's okay to assume the temperature is constant, and then the product of pressure times volume also has to be constant. So how can we use this equation? Well, it we will see in a second how we use it, but before we do that, yeah, it's better to do it now. So in the rest of my derivation, I will actually need the derivative of pressure with respect to time. Well, actually, even before I get to that, yeah, if P over V is constant, I'm going to call this constant A. It follows that yeah, dP yes, yeah. It follows also that dP over dV is equal to A. It's a constant. Okay, and so if I define some initial, you agree, right? Because obviously that means that P equals A times V. And so the derivative of P with respect to V is simply this constant A. Now, if I define some initial state of my system, okay, if at the beginning of my experiment, the pressure is equal to P0 and the volume is equal to a value that I call V0, then A is defined by that ratio, okay? And that ratio, P will change, V will change, but that ratio is not going to change. So basically,
Sir, I have a question.
yes, please.
I don't understand what is A.
Yeah, let's do it again. So basically, P times V is constant, it doesn't change.
Okay.
So that's thermodynamics, it's an empirical law. If you do this experiment with a lot of different gases and you change the pressure, if the temperature is constant, you increase the pressure, the volume is going to go down. Okay? So I can call it, I decided to call it Ka, but I could call it, what's a good number? C, okay, like constant. I just give it a name. But now my problem here is that I actually don't want to carry a constant like that with me, so I'm just going to play a little trick. I think I might actually have done something wrong with the next step, but we'll fix it in a second. So yeah, P is equal to C over V, and so BP over VP is minus C over V squared. Now it's making more sense. Oh, sorry, I was going a bit too fast. And so, yeah, so that means that basically, yeah, so Why am I lost now? Sorry. Yeah, okay. So now C is a constant, and so at the beginning of my experiment, C is given by the initial value of pressure and volume. Okay, so I can substitute that in here. Okay, so if I take the pressure, this derivative at the beginning of the experiment, this can cancel out, and I'm left with minus P0 over P0. Okay. So the one relatively difficult step here is to just differentiate this expression for P with respect to V, which is what I've done here. So, yeah. So, yes.
So I don't understand dP divide dV from C divide dV square. You can see on charts. I don't understand why.
You wrote what you wrote in the chat is this is we all agree on that, right? Up to here, it's fine. That's okay.
Yeah.
So all I'm saying, yeah. So all I'm saying is that how do I calculate a value for this constant C? At the beginning, at time 0, I define P as P0 and V as V0. Okay. So that means that if PV equals C, then at time 0, C has to coincide. At time 0, C is P0, V0. But C is constant. So C will stay the same forever. Okay, so now let's differentiate P with respect to V. This is correct. This is also correct. You agree?
Yeah.
And near the beginning of my experiment, at time 0, I can replace V with V0 here, and I'm left with minus V0 over V0. Okay? I think it's okay. But if you don't agree, I listen, because it's kind of a tricky step. But basically, why do I do that? It's just because later, like I was saying, I will need to differentiate pressure with respect to time. So I'm just preparing myself to do that. And it's useful to use the chain rule and to say that dP over dt is equal to dP over dV times dv over dt. So if I substitute this expression for dp over dv in here, I find that dp over dt equals minus v0 over v0 times the derivative of volume with respect to time. Now, in doing this, we are making the assumption, basically we are replacing this derivative with its value at t equals 0, which is the value at the beginning. Okay, when you start, for example, if you define that as the beginning of your experiment, when the speaker begins to move, or when your air gun injects some change of pressure into the water, okay, to generate some seismic waves, acoustic waves that then will become seismic. So basically, we do not want to go very far from this initial setup. Otherwise, this approximation here would not be valid anymore. Okay, so as is usually the case in the problems we are dealing with, we are talking about oscillations that are small compared to the size, the geometrical size of the problem we are dealing with. I think, no, that's okay. That's a good explanation as good as it gets for now. So, ingredient 1, Newton. Ingredient 2, thermodynamics. And then we have one third consideration to do before we can put everything together and introduce a differential equation that we can try to solve. So let's see. Now, yeah. So now let's look again at the deformation of our parcel of material. Actually, let's think, since we are dealing with the volume there, we have pressure, volume, velocity. So can we essentially, can we determine a relation between volume and velocity? If we could, because right now, you see, it's sort of like, this is not a linear system, but it's sort of like when you solve linear systems, right? Here, we have a first equation with this velocity and pressure. One equation, two things that we don't know. Here, we have a relationship between pressure and volume, but it does, for the time being, it doesn't help that much because, again, volume, how does volume change is something that we don't know. So, but it's proportional, the change in volume is proportional to the change in pressure. So if I could, you can imagine that basically both velocity and the change in volume are two ways to describe how the material is moving, okay? The pressure describes the force that we apply, that is applied, but velocity and volume both sort of describe a displacement. So can we maybe, by just doing some geometrical consideration, can we maybe find a relation between them And then basically, if we can write volume in terms of velocity, we'll have two equations and two unknowns. And that's a situation where we can probably simplify finally the problem. So how do we establish a relationship between velocity and volume? Well, let's think about a simple, just like we did for the string, let's simplify by thinking about just one element of mass, one element of your gas that's cubic. And let's see how we can write a change in volume. The idea when you solve this type of problems, and it's the same thing that we always do in continuum mechanics. Basically, you have a large medium whose motion you need to predict. But if you just take one little chunk, one little parcel of that medium, you can use Newton's laws, like we're doing here, to find an equation that has to hold at that place there, and that equation has to be true anywhere in the medium. So if you solve that equation, that's a good way to predict the displacement of the medium at any point. I'm basically repeating what I already said actually at the beginning, talking about how we wrote Newton's law for an individual point of coordinate x, y, z, which are not specified here, of the medium. So let's think about this point. So let's take a mass that is as small as we want, right? So to remind myself that it's small, I'm going to use a little delta here. So I'm going to call delta x, delta y, and delta z its sides. And I'm going to ask myself, how can I write volume in terms of its volume, in terms of its change in volume, in terms of its deformation. If I have, I call u the displacement, and with component ux, uy, and uz along the three axes, and of course then the velocity is nothing but the time derivative of the displacement. Well, then if I do that, or if you don't mind, since it's small, I'm actually going to call it delta u x, delta u y, delta u z, just to remind myself that we are talking about small displacements. So if I now think about this element here, and it's as small as I want, right? So if around here the displacement is delta ux, is delta u, then the component, in this case in the y direction actually, is delta u y. So this length here is delta uy. Okay, if some pressure came in and deformed my element of mass, and for some it elongated it for some reason, it can compress it. You have oscillation of pressure. Actually, pressure goes up and down. So in this case, we have a positive displacement here. I can take this mass to be as small as I want. That's the only constraint that I have. So it's okay to think that all over this little surface here, the displacement is constant, and I call it delta uy, the displacement in the y direction. So then the change in volume due to this displacement is delta uy times delta x times delta z. If the volume of this little parallelepipedus here, okay? Just the dashed parallel equilibriums. So now, exactly the same reasoning applies to the other two sides of this cube. Well, I should say to the other 5 sides of this cube. Okay. So, for example, now this is delta V with a capital V, the change in volume related to displacement in the y direction. And this is the change in volume associated with the displacement in the z direction, and it's delta uz times delta x delta y. Okay, delta x delta y being the area of this surface. And the same thing in the y direction. And actually, now that I think about it, why don't I do it in an even better way? It's the same thing, but I give you a bit more details. So I make a better drawing. So actually, let's call it U. And now, for example, in the x direction, okay, so or y direction, it's easier to draw. I have a displacement. I will observe some displacement on both sides of the cube, and it can be a bit different. So maybe on this side we have a compression that I call U. Y, and here I have an expansion that will be Uy plus delta Uy. Okay, so the total, if this is Uy and this is Uy plus delta Uy, the total change in volume will be associated with the deformation in the y direction will be Uy plus delta Uy minus Uy. Okay, this deformation minus this deformation multiplied by delta x delta z. Or in other words, what I'm doing is I'm calculating the volume of this guy here, and from it I'm subtracting the volume of this guy here. And that's really, okay, this is a bit more complete as an explanation. That would be the change in volume, I call it 1, associated with a deformation in the y direction. Let's call it 2, because y is the second of the Cartesian component. Okay. So I can do exactly the same calculation for the two other Cartesian axes. And I would obtain that V1 for the same reason, so this cancels out. Of course, that delta V1 is delta Ux times delta Y delta Z, and delta V3 is del U Z times del X del Y. Okay. I don't hear any complaints, so I'm assuming that you guys are still with me. So I will happily delete my beautiful drawing.
No.
What? A question?
Please.
No.
No.
Go ahead.
No, there is no question.
Okay. All right. So basically, here's the total change in volume. Of course, you know, we are simplifying things by reducing this to a cube. And you might be thinking, okay, but actually, the real deformation is not like I should be. I am. What I'm trying to say basically here is that we are allowed to simplify things in this way because we consider a very, very small elements of matter. Okay, so that allows us to think in terms of little cube and to neglect, for example, you know, I'm thinking that matter expands like this and like this. I'm not considering, you know, what happens here, right? But it doesn't matter because delta X and delta Z are so small that this is essentially zero. Okay, so we, and if it's not small enough, it doesn't matter because we can always go to the limit. Ultimately, what we are interested in are derivatives or differentials. So we can always bring it to the limit where it's essentially zero and our formula are good enough. Okay, so when you, if you feel a bit uncomfortable with these things, you always have to think, okay, but this really, it has to work only for very, very little elements of matter, not macroscopically, okay? And then you discover that it's okay. So the total change in volume is just the sum of these three differential volumes here, that is delta ux times the y times the z plus delta uy times the x the z plus delta uz the y the z. Okay, it doesn't look very beautiful, but now let's actually divide both sides of this equation by the initial volume, V equal the X, the Y, the Z, of my element of gas, of my element of mass. I divide both sides of this equation by V. Well, here the Y, the Z cancel out, and I'm left with delta Ux over the X, and here the X, the Z cancel out, and I'm left with delta Uy over the Y, and so on, and so forth. Now, this is the ratio of two increments, okay? Increment in displacement versus increment in distance. And so is this, and so is this. I just told you we can take these things as small as we want. We can basically go to the limit as the X, the Y, the Z tend to zero. So what we have here as just a derivative, the partial derivatives of the three components of displacement with respect to the three Cartesian coordinates. And if you remember my definition of the nabla operator, you will accept that it's okay to write this in this way. And I want you to be very careful with these things. Here, I have nabla and I have a scalar. Okay, P is not underlined, pressure is a scalar. So this is a vector. Okay, the gradient, the nabla applied on a scalar has to give me a vector. And we define once again that vector at the beginning of this the lecture today. Here, actually, I'm doing a different operation, okay? What I'm saying here is that this expression is what I obtain if I apply the nabla with a scalar product here, okay? This dot is not just a dot, it's important. It stands for scalar product. And that will be the scalar product of two vectors, which is the sum of the products of component by component of the two vectors. And this is exactly what I have here. Okay, the product of vector A times vector B is AX BX plus AY BY plus AZ BZ, sum of the products of the components. The nabla, it works in the same way, except that the nabla actually stands for the differentiation. Okay, so you are actually, it's not just multiplying, but you actually differentiate. But the rules that you apply are exactly the same. So vector, scalar product, and this is a scalar, okay? What you get here is a scalar, it's a number. It is how much the volume of these things changed. So this operation here is called divergence. And some of you probably heard about divergence. You were probably taught what divergence is before, but it might sometimes be difficult to form a straightforward, simple picture of what divergence means. Well, here you have one. In geometry, the divergence of the displacement that you might measure in space, if you have a mass of something that is deformed, the change of volume, the relative change of volume is the divergence of the displacement. So you can have displacement with zero divergence. It means that the displacement is constant in space. So your whole, like, if something moves without changing space, or each point forming, say, my marker moves in space without changing space. I'm not breaking it, I'm not compressing it, I'm not pulling it. The divergence is zero, okay? The shape is not changing. But if I move water around like this, the water inside my bottle has an important divergence because all the particles will be going in different directions if I shake it like this and stuff. Okay, so if you have a translation without deformation, the divergence within the object that's being translated is zero. If you have deformation, you will typically have some divergence, and the more important deformation you have, the larger the divergence. Well, or not necessarily. I mean, what I should say is not the larger the deformation, but if a deformation involves a change in volume, then you have a divergence. So maybe the water is not such a good example anyway, because the shape changes, but the volume probably doesn't change that much. I would have to heat it up quite a bit, maybe, to have a bit of an expansion or something like that. Okay, so you get the point, I hope. Questions? Good. So, okay, so here, so the bottom line of this last exercise here, we have a certain piece of information that we want to use. The relative change in volume coincides with the divergence of the displacement. In these few minutes that are left, I will try to put these three equations together. And on Friday, well, on Friday we'll attack the differential equation that is so obtained, but let's first obtain it. So I need to play, I still need to play a couple of tricks. If this is true, okay, then of course the change, the absolute change in volume rather than relative is V0, the initial volume, times the divergence of the displacement. So the time derivative of this guy sorry, no need. If I divide this by the time interval that's needed to achieve this change in volume, and then I let this interval go to 0, I get the derivative. And here, if I do the same thing with the divergence of the displacement, I can change the order of differentiation. And so here I get, instead of the divergence of the displacement, I have the divergence of the time derivative of the displacement, which is the velocity. Okay, so here I basically just wrote the same physics here, but written in a different way. Over time, a given change in volume, the rate of change in volume is proportional to the divergence of the velocity rather than the displacement. Okay? Molto bene. Now let's do what I basically anticipated. Let's look, you know, mathematicians will disagree, but I don't really believe in distinction between partial and total derivatives. So this guy can be substituted with this guy. The rate of change in volume with respect to time. So if I plug equation 3 here into equation 2, I get dp over dt equals minus P0, initial pressure, times the divergence of, no need for a bracket here, the velocity. Okay, once again, notice that I have two vectors here, two vectorial entities, but because they are multiplied together through a scalar product, the result is a scalar, which is good because on the left-hand side I have a scalar. If I have a scalar on the left-hand side, I have to have a scalar and not a vector on the right-hand side. Good. That's the first thing. And then let us differentiate this guy with respect to time. Okay, so on the left-hand side, I differentiate once more with respect to time, and I do the same thing on the right-hand side. P0 is just the initial pressure, so it's a constant. And here, if I change once again well, let's just leave it like that, d over dt divergence of v. Okay, but now let's look at equation 1 again. We see we have used 3 and 2, but we haven't used 1 yet. So let's use 1. Let's look at 1. If I take the divergence of excuse me. If I take the divergence excuse me, I had a moment of amnesia, but I'm right. If I take the divergence of this guy, so I take the divergence of the left-hand side, and I take the divergence of the right-hand side. The equation, if I do exactly the same operation on both sides, the equation is still valid. So here again, rho, we assume also rho to be approximately constant. The density of air or the density of water is not going to change a lot, just like temperature. So here I can change the order of derivation, and I get rho d over dt, and the divergence of the velocity. And this is an operator that's called Laplacian. So it's equal to minus the Laplacian of P. Okay, unfortunately, I need to make a little, to give you a little reminder, but let's do it very quickly. The Laplacian is just, if you take the scalar, the dot product, okay? And you can do it as an exercise this afternoon. The dot product of the nabla by itself is just del over the square plus del square del y square plus del square over del square del z square, and that's called the Laplacian. Okay, so notice that the Laplacian is not a vector anymore. Okay, you apply the Laplacian to a scalar, you still get a scalar. You apply the Laplacian to a vector, it means that you do it for each component separately and you get another vector. Okay, so it looks like things are working out fairly well. Let's compare. I'm going to call this equation 1. So let's now compare equation 1 here with equation 2. Well, actually with equation star, which is the equation we obtain by plugging 3 into 2. Well, now we have, in both equations, we have the divergence of the velocity differentiated with respect to time. So what about, from here, I just say, okay, then if I divide both sides by rho, the Laplacian minus the Laplacian of the pressure divided by the density gives me exactly this guy. So I can plug it in here. And that's the equation that I get. And I'm going to basically, as far as I'm concerned, I'm going to stop here for today, but I would like you to think a little bit about this equation this afternoon. It's very similar to an equation we've met before in the case of the string. Remember, if instead of pressure, you have the displacement at the point of the string here, okay? Here, this is the pressure in some place in the gas. If I replace it with a displacement somewhere on the string, and here instead of pressure, I have tension, which is sort of the same thing. It's the force per unit surface that we have in the string. And here again, displacement, it's the same equation. And of course, instead of the Laplacian, the second derivative with respect to distance, but the second derivative with respect to distance in 1D, remember the string problem is a one-dimensional problem, is sort of, you can also think of it as the one-dimensional Laplacian, just like a one-dimensional gradient is a derivative. Okay, so this is called 3D wave equation. And what we've just demonstrated is that the pressure in a gas has to change in time at a given point according to the 3D wave equation. So the implication is that if you set some part of a gas in motion, waves will propagate in it in exactly the same way as we've seen before, except that now we are in 3 dimensions instead of 1 dimension. Okay, so if you have any comments or questions, please go ahead. Or if you don't, but you feel confused, prepare your questions for Friday morning.
Sir, I just wanted to ask if the negative sign should be there, or because I tried it in my notes and I think it's positive in the 3D wave.
I will double check because I'm pretty good. Yeah, I think you're right. I think you're right. So where does it go away? Oh yeah, because there's a minus here and there's a minus there. So
Yes, yeah.
obvious. Thank you. Thank you. Anything else?
Sure.
Yes.
You said this is a 3D wave equation.
Yeah.
So it's applied only in a gas?
Yes, well, so good point. So
Or we can apply it in a solid
so
state?
the point is that there are two ways to answer your question. So the first is that we will do the solid properly next week. And maybe
Okay,
already
yeah.
Friday we will get started. So the difference, of course, is that pressure does not really describe the stress that you have in the solid, because in the solid you have compression and expansion, but you also have shearing.
Yeah, yeah.
In the fluid, if you shear a fluid, it's not going to propagate a wave. Even if you could shear a fluid, it doesn't propagate a wave because there's no resistance. Okay, so if you could apply some sort of shearing forcing to a fluid, it will just end there. Okay, except that it's impossible in practice to generate shearing without perturbing the pressure as well, because you have to do some kind of so in the solid, if you shear, there's also a response to shear. The solid does not want to be sheared, and it will try to resist that. And from this resistance, a wave is generated, actually. So in the solid, you have that. This basically describes the propagation of a compressional wave, but you also have a shear wave. Okay, you cannot have a compressional wave alone in practice.
Yeah.
Un minuto. All right. So I think you can use, in a first approximation, you can use that for a solid if you only care about P waves. And if you, instead of P0 over rho here, you have to have something else. Okay, you have to have the P velocity squared.
Yeah.
We will see that in detail next week.
Okay.
So there are, you will find in the literature papers that do that, okay, especially in seismic exploration, since people often just look at the P wave, you can basically just describe the medium acoustically. But when you do that, you have to keep in mind that it basically neglects the shear wave altogether. It also depends on how you excite the medium. If you have just a simple explosion, which is similar to, it's like creating some mass or expanding a certain part of the medium in all directions at the same time, then you have very little shearing, basically zero shearing, and in that case, the acoustic description is okay. But it is not theoretically correct. It's an approximation that works. Okay?
Okay. Okay, thank you, sir.
Thank you. All right, guys, it's late. I have to go to another meeting. I'm ready. I'm happy to take more of your questions on Friday. All right, think about all these, and you will ask me on Friday if you want. Bye.
Okay.
Have a good day.
Goodbye, sir.
Thank you, sir.